Yeah, AgNO3 is correct. Silver nitrate. Sodium hydrogen phosphate. Is that monohydrogen or dihydrogen? It didn't specify, so if you're going to guess, I'd guess monohydrogen. Well, what is hydrogen phosphate? HPO4. What's the charge? No, phosphate's 3. But if you add an H plus to it, you're going to make HPO4 with a charge of... Sodium is what? So yeah, it's Na2HPO4. Sodium hydrogen phosphate or calcium bromate. It's calcium bromate. CaBr2 is called something else. What is CaBr2 called? CaBr2 is called calcium bromide. Calcium bromide. What is calcium bromate? That's correct. CaBrO3(2). Calcium bromate. Ammonium sulfite. Are these kind of easy? If they're kind of easy, then you want to skip ahead. So the nomenclature is down. Actually, the nomenclature was the previous chapter, chapter 6. So this is more practice with the nomenclature. We can skip the nomenclature as well if it's pretty easy. The ammonium sulfite is, what is that? NH4. NH4(2)SO3. And so this is kind of like a chapter 6, chapter 7 kind of review. But is this useful or not that useful? It's useful? You guys want to continue this or? No? Okay. All right, so what we're going to do is, this is what you can do on your own. I don't have to go through this because you do have the answers back here as well. Do that. There is one that I'd like to do, though, that's a little different. That would be number 60. I'd like to do this because I didn't talk about this in class. I want to do this one. But these are a lot of nomenclature practice in chapter 7 as well as chapter 6, and then some calculations. Number 60 is determine the empirical formula. So what is the empirical formula for this compound? It's a compound that contains 39.12% carbon, 8.772% hydrogen, and 52.11% oxygen by mass. And so, we'll go on. The first step is we assume a 100-gram sample, so it's going to give us 39.12 grams of carbon, 8.772 grams of hydrogen, and 52.11 grams of oxygen. And then empirical formula is as simple as mole ratio. So we got to go from grams to moles. We go from grams to moles by using molar mass. The molar mass of carbon, there's 12.01 grams of carbon atoms, or mole of carbon atoms. For hydrogen, it's 1.008. We're going to use this one rather than 1.001 because this is standalone. So 1.008 grams of hydrogen for every mole of hydrogen atoms. And this is wrong. This is wrong because this grams times grams will give me grams squared. Right? So this is not a gram to mole conversion. I got to cancel out the grams. And so what I have to do is I just have to flip this upside down so that I have a mole of carbon up here for every 12.01 grams of carbon. Now the grams of carbon cancels and leaves me with moles. I made the same mistake here. I want to go with moles of hydrogen. So moles of hydrogen is 1.008 grams of hydrogen. And then oxygen, a mole of oxygen is 16.00 grams of oxygen. All right, so we figure out the moles, and then we just get the simplest mole ratio. That would be the formula. Simplest whole number ratio. So this is 39.12 divided by 12.01. This gives me 3.257. I'm allowed 4, so 3.2572 moles of carbon. 8.772 divided by 1.008. This is 8.7023 moles of hydrogen. And this is 5211 divided by 16. This gives me 3.2568 moles of oxygen. And so formula is the mole ratio or atom ratio. So I get carbon 3.2572, hydrogen at 8.7023, and oxygen at 3.2568. But these aren't whole numbers, so how do I get these into the simplest whole number ratio? I divide by the smallest. This is going to be the smallest, so I'm going to divide by 3.2568. So if I do that, let's take 3.2572. 3.2572 divided by 3.2568 gives me this 1.0001. Hydrogen 8.7023 divided by 3.2568 gives me hydrogen at 2.6720, and then oxygen will be 1.000. And so what should I do? This number, should I round it to 3 or multiply by a factor? What I mean by multiply by a factor is this. What I have here is a fraction. So, for example, if I end up at x.3, x.3 is 1/3. And so to get rid of that fraction, I'd multiply by 3 times. If it's 0.5, it's halfway, so the fraction's a half. So I'd multiply by 2. If it's x.67 or 66 or 0.7, then that's 2/3. This is 1/3, 1/2, 2/3. If it's 2/3, I'd multiply by 3 times. This is 0.67, which is 2 2/3. 2 2/3 is the same thing as 2 2/3 is the same thing as 8/3. And so, in other words, I have C, H, C1, 0.000, H, 2 2/3. 2/3 is 0.67. O, 1.00. Well, 2 2/3 is the same thing as C, H. 2 would be 8 6/3. 6/3 plus 2/3 is 8/3. O. And so, do you see, I want to get rid of this fraction. To get rid of this fraction, I multiply by 3. And so that's C3H8O3. And then I get the simplest whole number ratio. Now, I would do that over here. And so this is just the side here. And so I see I'm at 2/3. And so what I'll do is I'll just multiply everything by 3. And so I'm going to get C3 and then H. Well, what is 2.672 times 3? It's 8.016. So I'm actually going to multiply it out because, so I'm going to get C 3.0003, H 8.0161, O 3.000. So I multiplied each of those numbers by 3 because I see it's this type of fraction. And then I'm going to round it. And so this is going to come out to C3H8O3. This would be the empirical formula. All right, that's the empirical formula. And then in the next section, we have a molecular formula determination. And so molecular formula is the same thing. We generate the empirical formula, and then we determine the empirical mass. The empirical mass is how much does the empirical unit weigh. The empirical unit would be the simplest whole number unit, and then compare it to how much a molecule weighs. If they weigh the same thing, then the empirical formula is the same as the molecular formula. If they weigh different, let's say the molecular formula weighs 2 times more, 3 times more, 4 times more, then the actual molecule is a lot bigger than the empirical unit. And so we'd multiply by that factor. So that's pretty much it here. 67 is some more definition. 72 is a more advanced, but not really that advanced. This is a mixture. You know, important mixtures like air we can treat a little differently than a typical mixture. So for air, they know the Avogadro's numbers worth of air molecules, which would be nitrogen and oxygen molecules, weighs about 29 grams. So they have the molar mass of air. Normally when we think about molar mass, we think of molar mass of a pure substance, like a compound or element. In this case, this is the molar mass of a mixture. So, well, the molar mass is not fixed. It's going to change depending on the composition of the air. And so they just say approximately 29 grams for every mole of their molecules. So this is another interesting one here, 72. You can take a look at that. But yeah, this is kind of what you do, you know, to help reinforce, you know, what you read in the chapter. So we're good with skipping. Seems like people want to skip this, so I'm going to skip this. And we're going to go to chapters 8 and 9. Chapters 8 and 9. We looked at electrolyte properties last time. And so what we're going to do today is we're going to look at reactions in detail. And you know, earlier all we did was we tried to get a feel for chemical properties, you know, how reactive these types of things are. In this case, what we're going to do is we're going to actually look at individual reactions and analyze them. And so let's here I'm going to kind of go and converge with your book more as the presentation goes. Not exactly with your book, but we're looking at metathesis reaction. And so this is not going to be in the same order as your book, but metathesis reactions, switch it over here, are termed ion combination or favorable ion combinations. And the most common pattern that we see is something called a double replacement, a reaction. So let me show you that here. And so if we take two ionic compounds, you know, this has cation A, anion X, cation B, anion Y, and then we try to mix up the partners and see if we can come up with an even more favorable combination. How do we know it's a favorable combination? One way of knowing it's a favorable combination is it forms a precipitate, but that's not the only way we know. And so what we have here is the most common. I don't call it double replacement, I call it metathesis. Why do I call it that? Because if I start calling it double replacement, then you're only looking for double replacement, and that boxes you in, you know. Whereas, you know, metathesis might not look like a double replacement, but it is. And so we don't always look for a specific pattern. So the reason I call it metathesis is A plus BY plus CZ. You know, if I just threw in a third compound in there, people go, wow, that's impossible. Because they're only used to an A plus BY. But if I did an AX plus BY plus CZ, then it's impossible. But in reality, it's so easy. Because all you're looking for is you're looking for the right cation and the right anion to come together to react. And so it doesn't matter how many. I could put in tons of reagents, these, you know, chemicals in here, and all I'm trying to do is pick and choose, you know, what cations, what anions might come together to react. And so I've done this. I did this in Chem 1A. I did this in Chem 1A where I threw in 3 and see how many people left it blank. Lots of people left it blank because this doesn't fit their pattern, their box pattern. All right, but learning patterns is easy, right? And so we can learn this pattern. So a common pattern is this, the AX plus BY. If we want to see if a reaction occurs, then all we do is we switch. We either switch the cations or we switch the anions. The easy thing to do is just to switch the anions and see if that results in a favorable combination. And so what we do is we go AY plus BX. Does that result in a favorable combination? I don't know. We have to analyze it. And so is this a favorable combination? How do I know it's a favorable combination? One, it's a favorable combination if I get precipitation. PPT is the abbreviation for precipitate. But precipitation, how do I know it will precipitate or won't precipitate? I would know it by the solubility rules. And so I just look at the solubility rules. There are other favorable combinations. Another favorable combination is if it makes something like this. If we go from a stronger acid on the left to a weaker acid on the right. The left is called the reactants, the right is called the products. And so maybe one of these is an acid over here, and we have an acid over here. If we're going from a stronger acid to a weaker acid, that's a good combination. Because weaker acids are a good combination. They're harder to break apart. Stronger acids are very easy to break off the hydrogen ion. And so this is a favorable combination. Three is gas formation. If a gas is formed, then we're good. And some of these are overlapping, gas formation. So for example, H2CO3. If H2CO3 is a product, that's good. Because what happens is H2CO3 is unstable. And so the ultimate product would be H2O liquid plus CO2 gas. So here's my gas formation. Product decomposes. So that's very favorable. Or sometimes I'll have a product like H2S. H2S, this is a gas, etc. If there's no favorable ion combination, then there's no reaction. If no favorable combination, then no reaction. And so what we call these, 1, 2, 3, these are called driving force. Driving forces for reaction. And all we need is one of them. We don't need all three. Just one of them will drive the reaction forward. Precipitation is one of the most common. So you learn the solubility rules. Do you want to learn this set of solubility rules? Did I already mention this one? It's a lot of work to memorize this. No, you'll memorize the ones. We'll do that and we'll just summarize it like this. We'll do the summary of the solubility rules here. And so this is part of what's called data reduction. Data reduction is you take a lot of data and then try to reduce it to something more digestible. Yeah. All right, so let's take a look. Solutions of lead-2 nitrate and sodium bromide are combined. Okay, don't worry about this net ionic, which we'll talk about in a minute. Yeah, but what we want to do is we want to see, will I get a favorable ion combination? Because lead-2 nitrate's ions, sodium bromide's ions, so maybe I will get a favorable ion combination. But is lead-2 nitrate itself a favorable ion combination? And so what is lead-2 nitrate? What's the formula? Good. And it's a solution, so it's dissolved in water, so it's aqueous. Now what does a solution consist of? Well, it's a nitrate salt. Nitrate salts are all soluble. And so if I were to look at this in a beaker, what I have here is this a strong electrolyte, non-electrolyte? What is it? Weak electrolyte? Strong, weak, or non? It's a strong electrolyte. Strong electrolytes are ionized. So there's lead ions and nitrate ions floating around in here, moving about. And so, is this a favorable ion combination? Not really, because the ions are separate. They aren't paired or together, right, to form a lattice. The only time these ions will come together to form a lattice is if you evaporate all the water, and then you'll have salt crystals. Salt crystals are just ionic compounds that are not acids. And so this is not what we call a favorable ion combination because they're all separate. Plus sodium bromide. What's the formula for sodium bromide? NaBr. Br2. Is that right? NaBr2? No, that's wrong. Let's fix it. It's just NaBr. Okay, it's also a solution, so it's AQ. If you like that. Now, is it soluble? Yes. Is it a strong, weak, or non-electrolyte? It's a strong electrolyte. How do I know? Because I know what the strong electrolytes are. What are the strong electrolytes? Strong acids. Strong acids. Strong, yeah, but what are the strong electrolytes? Strong acids. Strong bases and strong acids, strong bases, and soluble salt. So sodium bromide is a soluble salt. So it's a strong electrolyte, which means it's dissociated in solution. Then we mix these two solutions together. When we mix the two solutions together, then all the ions are mixed together in one pot. And so we got lead ions, we have nitrate ions, we have sodium ions, and we have bromide ions. Do you see any favorable ion combinations? We could try sodium with bromide? No. The only time sodium with bromide come together is if all the water evaporates. I'm sorry? Lead and bromide. Lead and bromide is a favorable ion combination. But lead is a 2+. How many bromides will we need? 2. And so lead and bromide are favorable because lead bromide precipitates. And so what we end up with here is we got lead with bromide ions. And what's left over? Sodium with nitrate ions. But sodium with nitrate ions, those are just, they aren't coming together. So those are still in water. Sodium nitrate's being a strong electron. Lead bromide is going to precipitate. But now the atoms aren't quite balanced because we need 2 bromides. In order to have 2 bromides, we must have had 2 sodiums. And then that means we had 2 sodiums here and 2 bromides here. That means we have to have 2 NABRs here. And if we have that, that's going to give us 2 sodiums and 2 nitrates, which we have here. And so this is a favorable ion combination. This is what we call a precipitate here. So that's good. It's favorable. Now what we want to do is we want to detail this reaction in more detail. That is, for example, this. This is what we call a complete or conventional equation. Then what we're going to write is something called an ionic equation. Ionic equation, the rule is very simple. For the ionic equation, the IE, we ionize only the strong electrolytes. We already did that here. So if we ionize the strong electrolytes here, what that means is that we've dissociated into ions. So PbNO3 will break up into Pb2 plus 2 NO3 minus. And so that's lead 2 nitrate. And then over here, sodium nitrate, that's a strong electrolyte, that's going to break up into 2 sodiums plus 2 bromides. Is lead 2 bromide, this is going to come together with this and it's going to precipitate out. It's lead 2 bromide solid. Is lead 2 bromide a strong electrolyte? Well, we ask ourselves, is it a strong acid? No. Is it a strong base? No. Is it a soluble salt? No. Therefore, it's not as strong. If it's not a strong electrolyte, leave it alone. So this is going to come out to PbBr2 solid. Sodium nitrate, is that a strong electrolyte? Is it a strong acid? No. Is it a strong base? No. Is it a soluble salt? Yes. So we ionize it. 2 sodiums and 2 nitrates. 2 sodiums and 2 nitrates, and then that's it. And so this is called the ionic equation. Now, take a look at what happened to the nitrate. Did anything happen to the nitrates? So we started off with 2 nitrates here, and we end up with 2 nitrates here in solution. So what we say is that we say the nitrate is a spectator because nothing happened to it. The lead is not a spectator because something happened to the lead. And so the nitrate is a spectator. What about sodium ions? Are sodium ions spectators, or did they actually react? Spectators. So the sodium ions and the nitrate ions are spectators. They started off in solution and they end up in solution. What about the bromides? Bromides are not spectators. And so the NIE, the net ionic equation, gets rid of the spectators. And so if we get rid of the spectators, it's only the lead ions that, like the bromide ions, to react to form lead-2 bromide, precipitate. And so this is what would be called the net ionic. So any lead ion from any source will react with bromide ion from any source to precipitate. So that's it. So here, this is called the conventional or complete equation. And then we see the driving force. The driving force is the precipitation of the lead-2 bromide. Here, there's a certain, if it's precipitate or not. And then we write out the ionic equation. Here's the ionic equation. Then we get rid of the spectators. Come up with the net ionic equation here. All right, we don't have to have a precipitate. We can go to, from a stronger acid, it doesn't have to be strong, from a stronger acid to a weaker acid. Stronger acid to weaker acid may not result in a precipitate, but will drive a reaction forward. And so let's take a look at this. Hydrochloric acid and sodium. I think that's an error. The sodium hydroxide. Didn't fit. So let's do hydrochloric acid and sodium hydroxide. Hydrochloric acid, what's the formula? HCl. Sodium hydroxide, what's the formula? NaOH. So what we do is we just switch the anions. And so this would be the hydrogen ion with the hydroxide ion. Hydrogen cation with the hydroxide anion makes HOH. HOH is H2O. And then sodium with chloride. Now we ask ourselves, is there any precipitate here? Well, this is dissolved in water. This is dissolved in water. Sodium chloride, is that soluble? Or is it a precipitate? It's soluble. And water is just what we call a liquid. It's not going to form a precipitate. And so there's no precipitation that occurs here, but there is driving force. What is the driving force? The driving force is this. We're going from a stronger acid here. Stronger acids are highly reactive. To a weaker acid is stable. And so the weaker acid is what? No, water. And so water is very weak acid. We don't really normally consider it very acidic. There's a stronger acid to weaker acid. Water's on your list of acids. Right? You recall seeing it? Yeah, okay, then I'm not going to bring it up. And so if we're going from stronger acid to weaker acid, this is a driving force. All we need is one driving force, and therefore this reaction should occur. In other words, we're going from an unstable combination, very reactive combination, to a very stable combination. Salt water is stable. So this is the complete equation. Now the ionic equation is simple. We just ionize the strong electrolytes. Is HCl strong acid, strong base, or soluble salt? Yeah. This HCl is a strong electrolyte, so it ionizes into H plus Cl minus. Is sodium hydroxide what is sodium hydroxide? Strong acid, strong base, or soluble salt? Soluble salt. So it's going to break up into sodium ions and hydroxide ions. Hydroxide itself is a strong base. Water, is that a strong acid? No. Strong base? No. Soluble salt? No. So water we leave alone. Sodium chloride, is that a strong acid? No. Strong base? No. Soluble salt? Yes. So we dissociate that. Sodium plus Cl minus. All the atoms are balanced out, so we didn't have to do what we had to do in the last one. Are there any spectators here? Yeah, it looks like chloride, nothing happened to that. And sodium, nothing happened to that. And so the net ionic equation, we ignore the spectators. We just look at what reacts. H plus reacts with OH minus to form H2O liquid. So this would be the reaction here. Ah, very good. The last one is the gas formation. There are two, actually three things that are unstable. What are they? Okay, this is a good ion combination. Let me just show you. H plus ions and carbonate's good. H plus and carbonate forms carbonic acid. Carbonic acid decomposes into CO2 and water. So this is driving force, CO2. Yeah. This is another good ion combination. H plus and sulfite. H plus and sulfite makes sulfurous acid. Sulfurous acid decomposes into sulfur dioxide and water. So again, this is a gas. Ammonium and hydroxide like each other too. Ammonium and hydroxide form ammonium hydroxide. Ammonium hydroxide decomposes into ammonia and water. Ammonia is very soluble, so it's AQ, but it can be driven off as a gas. So these are ones that form unstable products or potential gases. It could also be thought of as going from stronger acid to weaker acid, as we'll see. So let's look at the reaction between sodium carbonate and hydrochloric acid next. Okay, sodium carbonate is, what's the formula for sodium carbonate? NaCO3. Is that correct? Yes. Na2CO3 is correct. Because carbonate's -2, sodium's +1. So we need 2 of the sodium to balance out. Okay, this is aqueous plus hydrochloric acid. HCl. So what we're going to do is we're going to switch the anions. I'm going to form sodium with chloride. So that's sodium chloride. But the atoms aren't balanced. I'm not going to worry about the balancing until after I get the correct formula. So you might say there are 2 sodiums. So you wouldn't do this. You wouldn't do NA sub 2. We want to make sure the formula is correct. And then the hydrogens with the carbonate. If we have hydrogens with carbonate, hydrogens plus carbonate's 2, so we'll need 2 hydrogens. Balance that out. We form hydrogen carbonate or carbonic acid. But carbonic acid is unstable. What does carbonic acid do? Carbonic acid decomposes immediately into H2O liquid plus CO2 gas. And so here I have my driving force. Driving force is gas formation. I'm going to get effervescence. But these aren't balanced. I need 2 hydrogen ions for every carbonate, so I need to multiply this by 2 HCl. And that's going to leave me with 2 chlorides, so I got to multiply that. And so now everything's balanced. Looks good. And so let's rewrite this. Sodium carbonate aqueous plus 2 HCl aqueous yields 2 sodium chloride aqueous plus H2O liquid plus CO2 gas. This would be the complete or the conventional equation. It's balanced. What I mean by balance is that there are 2 sodium atoms here, there's 2 sodium atoms here. 1 carbon, 3 oxygens, 3 oxygens, 2 hydrogens, 2 chlorines, 2 chlorines. So all the atoms are balanced. Now in the ionic equation, we ionize the strong electrolytes. So sodium carbonate. Is sodium carbonate a strong acid? No. Strong base? No. Soluble salt? Yes. And so this is going to break apart into ions. It's going to break apart into 2 sodium ions plus 1 carbonate ion. We know we need 2 sodiums to balance out that -2 charge on carbonate. Now the HCl has 2, but it's 2 of each. So we got 2 H pluses plus 2 chlorides. These are all aqueous. Okay, this is going to go to sodium chloride. Sodium chloride is a strong acid? No. Strong base? No. Soluble salt? Yes. So it's going to go to 2 sodiums and 2 chlorides. Water is a strong acid? No. Strong base? No. Soluble salt? No. Leave it alone. CO2, strong acid? No. Strong base? No. Soluble salt? No. Leave it alone. CO2 gas. Okay, then we look for spectators. Are there spectators? Things that didn't change. Sodiums. Carbonates, H plus changed. Chlorides didn't. And so we get rid of those spectators, and we just go carbonate plus 2H plus yields H2O liquid plus CO2 gas. This would be the net ionic equation for this reaction here. They didn't even bother writing carbonic acid. Take a look. The second product is the hydrogen cation with the carbonate anion, which makes carbonic acid, which they didn't bother writing because actually there's no use in writing it. It decomposes immediately to form CO2 and water. We just wrote it because it's a helpful guide to how it reacts. And then we have they call it the total ionic equation, I just call it the ionic equation. And then the net ionic equation. All right, are we out of time? Yeah, fine. Two more minutes. Your book, your book divides things into categories. Let me just finish off with this. So do you want to memorize all these categories? This is one category. Double replacement reaction with undissolved reactants. Ion combination reaction in which one of the reactants may not be in the form of a solution. Description of reactions will indicate the state of its reactants as solid, liquid, or gas. Example, reactions that occur with compounds that are insoluble in water but react with acids. Do you want to memorize that category? No. It's much simpler than that. So this is just a bit much. So we'll talk about this one. This one's actually not difficult because we look at all the reactions the same way. Okay, so I'll stop here. Let's do the lab.